Hello, my name is Yaroslav Akatyev. I'm a researcher from Wireless Networks Lab in the Institute for Information Transmission Problems of the Russian Academy of Sciences. In this video, I'm going to demonstrate to you a testbed that allows experimentally studying the feasibility of off-the-shelf mobile devices to perform an asynchronous multi-link operation. The multi-link operation is a new technique proposed in the 11B amendment and designated to improve throughput and reliability of future Wi-Fi networks. The core idea of multi-link operation is to exchange data simultaneously in several separate frequency channels from one band or different, for example 2.4 and 5 GHz. If channels are used independently, the data can flow in these channels in different directions, so this mode of the multi-link operation is called asynchronous. However, simultaneous transmission and reception in some circumstances may lead to inter-channel interference that may corrupt the frame received. In this case, to prevent the interference, synchronous mode can be used when all data flows have the same directions at any specific moment. This mode provides less benefit than the asynchronous mode. So, question arises: under what conditions which mode can be used? In our research, we have decided to create a testbed that would help to find an answer for this question. Our testbed is designed to evaluate how current user mobile devices are compatible with the asynchronous multi-link operation. The scenario under scope is a network of two multi-link devices, a station and an access point. Because there are no devices supporting multi-link operation on the market, we use two access points to model one multi-link AP that can independently operate in two channels from one frequency band. To model multi-link stay, we use two smartphones connected to different APs. This approach allows us to set up separate data transmission in two channels. The first channel is downlink, where frames are transmitted from AP1 to stay 1. The second channel is uplink, where state 2 continuously transmit frames to AP2. We mimic multi-link devices of various sizes by placing the smartphones at different distances from each other. During the experiment, we measure the throughput of the downlink channel that can decrease due to interference from the transmission in the uplink channel. We set appropriate level of throughput reduction to no more than 10%. We conduct our experiments in Uni 2C and Uni 3 bands because combining them gives the longest portion of 5 GHz spectrum. We use saturated UDP traffic in both channels for experiment. To generate and process it, we use Python scripts and special binaries compiled for access points. We make sure that the transmission in the downlink channel doesn't influence transmission in the uplink channel with a laptop in monitor mode that allows capturing all frames transmitting in a certain channel. Let's move to the results of our experiment. The first plot shows throughput dependence of the downlink channel on spectral distance between the channels. It illustrates the case when smartphones are placed at 30.5 cm apart. This distance corresponds to the typical size of modern smartphones. Different colors refers to different bandwidth of the uplink channel that creates interference, 20, 40 and 80 MHz. The blue line shows the throughput of the downlink channel without interference. When the bandwidth of the interfering channel increases, the side lobes of the signal spectrum expand. As a result, throughput is reduced at greater spectral distance. Further, the throughput fluctuates about constant value, but even with a spectral distance over 300 MHz, the throughput reduction remains greater than 25%. The next plot depicts results of the second part of our experiment. Now the distance between smartphones equals 30 cm, which corresponds to a typical size of laptops. Greater distance between antennas help to suppress inter-channel interference. As a result, at spectral distance greater than 125 MHz, throughput recovers to the level of the channel without interference. Our results show that the limited size of modern smartphones doesn't allow negating interference even at a sufficient spectral distance. Consequently, the implementation of the asynchronous multi-link operation in Unit 2C and Unit 3 bands for smartphones remains questionable. However, for laptops, antennas can be separated sufficient to eliminate the negative effect of the inter-channel interference. So, the asynchronous modelling operation can be implemented in these bands for laptops. To sum up, the larger modelling devices can be implemented with current technologies, but smartphones, the most ubiquitous mobile devices, need a new design iteration. Thank you for watching.